Hello, welcome back. In this video we'll discuss the conductivity in solid electrolytes. The solid electrolytes are a class of materials that conduct electricity by means of movement of ions in their solid phase. The solid electrolytes are defined in this fashion. The solid electrolytes are a class of materials that conduct electricity by means of movement of ions in their solid phase. So these are a class of materials that conduct electricity by means of movement of ions in their solid phase. And these materials have a striking difference between the other materials such as metals and semiconductors. These materials have a striking difference between the metals and semiconductors, where the conductivity is mainly due to the electronic conductivity can be seen. Whereas in the case of solid electrolytes, the conductivity is mainly due to the ions. Solid electrolytes conduct electrical current by movement of ions, that is analogous to the liquid electrolytes or liquid electrolytic solutions at ambient temperature. The solid electrolytes are also called as fast ionic conductors, FIC, or super ionic conductors. These are the two other names for the solid electrolytes. These materials, they have high ionic conductivity and very small electronic conductivity. Again, in solid electrolytes, the ionic conductivity varies from material to material. The ionic conductivity of solid electrolytes acceptable for energy applications can originate from three different mechanisms. Ionic conductivity mechanisms in solid electrolytes. The first one is the number and nature of point defects, line defects, and planar defects. Secondly, a unique phenomenon which can be roughly described as a corporative behavior of specific structural units in solids facilitating fast ionic transport in superionic phase. The second mechanism is a unique phenomena which can be roughly described as corporative behavior of specific structural units in solids facilitating fast ion transport in superionic phases. In the superionic phase, certain structural units, they exhibit corporative behavior. The corporative behavior of the structural units will contribute to the ionic transport in superionic phase. The third mechanism is superstructures consisting of highly conductive and non-conductive fragments are responsible for the ionic conductivity. The conductive superstructures are responsible mainly for the ionic conductivity, while the non-conducting superstructures are responsible for maintaining the physical structure of the material. Superstructures consisting of highly conductive and non-conductive fragments. The non-conducting fragments are responsible for the mechanical stability and stability against degradation caused by external physical and chemical factors such as high temperature, high energy radiation, and exposure to reactive substances. The third mechanism that is used to explain ionic conductivity is superstructures consisting of highly conductive fragments. And we'll have two different types of superstructures in a solid electrolyte. The first one is conductive superstructures, the second one is non-conductive superstructures. The conductive superstructures are responsible for the ionic conductivity, while the non-conductive superstructures are responsible for the mechanical stability and stability against degradation caused by external physical and chemical factors. Of the three different mechanisms, in this video we'll discuss the first mechanism, that is the ionic conductivity dependence on the number and nature of the defects. We'll start our discussion with point defects. What are point defects? Point defects are those missing atoms or extra atoms or ions at the lattice points. There are two major point defects that we come across in the discussion. They are Schottky defects and the Frenkel defects. In the case of Schottky defects, an atom or an ion will be missing from the regular structure. We have circles filled with gray color and circles filled with white color. There are also circles that are constructed using dotted lines. So dotted circles, here is one more dotted circle. At these dotted circle sides, the ions are missing or the atoms are missing. So we have two-dimensional single crystal, something like this, in which we have two different atoms or ions. We are representing them using circles filled with gray and circles filled with white color. In this arrangement, we find at this location where we have the dotted circle, atom or the ion is missing at this site. Similarly, if you go to the fourth row, here also you will find one more. So at the lattice point, you have a missing atom or ion. It is called a Schottky defect. It is occurring at one particular lattice point, so we call it as a point defect. And in the case of a Frenkel defect, you see you have a filled circle here, another filled circle, but in this structure here we should be having a filled circle, but that filled circle is missing and it has come to this location. From the regular structure, the atom or the ion, it moves into an interstitial. So this is what is called as an interstitial. So it moves into an interstitial location, leaving one vacancy here. Here we have a vacancy. Corresponding to that vacancy, we have an interstitial. And the pair of these defects are known as Frenkel defects. So there are two Frenkel defects in this structure. And in this structure, you have two Schottky defects. Next, we discuss the line defects or dislocations or linear defects. Consider this as a three-dimensional crystal. In this, along this particular vertical line, the atoms are missing. Along one particular line, since it is happening, we call it as a line defect. So the kind of defects result from missing ions in crystal structures along a line. The ions or atoms are missing, then we call them as line defects or linear defects. And one such linear defect is a dislocation. Now we shall see the third defect, that is planar defects. So defects that occur on a plane, one example is grain boundaries. Here you see the entire material is divided into unequal grains of random shape. Each such small region is known as a grain, and the boundaries of the grain are known as grain boundaries. The grain boundaries are considered to be highways for the ions. For ions, the grain boundaries are the places where the ion mobility must be the highest in the most defect-rich directions at the interface. Now we shall write the conductivity expression. The conductivity sigma can be written as Ne mu, where N is number of charge carriers, E is their charge, mu is mobility. The mobility mu depends on temperature, crystal structure, and it is a complex function of both temperature and the structure. Using this diagram, we'll try to understand ionic conductivity mechanism using the defects. Here we have a vacancy. There are two ions in the crystal. The ions are A and B. Suppose ion A, if it were to go to the vacancy, then it depends on the activation energies of the site, the potential of this site. This site is just similar to the site of the ion A. So the ion can hop into this particular site. A possible transfer of an ion A from its original position to a point vacancy can be seen here, and the probability of this jump will depend on the nature of the surrounding ions, the distance between initial and final points. The parameters of the lattice also plays a major role. Apart from these, temperature is an important factor to affect the hop. Using this mechanism, one can write conductivity sigma as sigma 0 exponential minus EA upon RT, where R is universal gas constant whose value is 8.31 joule per Kelvin per mole, and EA is the activation energy, T is the temperature, In this video we have seen what solid electrolytes are. Solid electrolytes are a class of materials that conduct electricity by means of movement of ions in their solid phase. The electrical conductivity is different from that of the metals and semiconductors, where electrical conductivity is mainly due to the electronic conductivity. We have said that these materials are also called as fast ionic conductors or super ionic conductors. These materials will have high ionic conductivity and very small electronic conductivity. The high ionic conductivity mechanism can be explained using the number and the nature of the point defects, line defects and planar defects, a unique phenomenon which can be roughly described as corporative behavior of specific structural units in solids that facilitates fast ion transport in super ionic phases. The superstructures consisting of highly conductive and non-conductive fragments are also responsible for the high ionic conductivity. In this video, we will discuss the number and nature of the point defects, line defects and planar defects influence on the conductivity. We have seen the point defects, we have seen the line defects, we have seen the grain boundaries. We have said that grain boundaries can act as highways for the ions in the ionic conductivity. We have written the ionic conductivity sigma as Ne mu, where mu is the mobility, E is charge of the carriers, N is the number of charge carriers. Mu is a complex function that depends very much on the temperature and the crystal structure. We have seen a mechanism where an ion can move from one point to the other point in the space lattice. We have written an expression for the conductivity. Sigma is equal to sigma 0 exponential minus Ea by RT, where R is the universal gas constant, Ea is the activation energy, T is the temperature. Thank you.